is we get 2am over h bar to the 1/2, and I'm just gonna throw this guy out there. So I'm just throwing this guy outside of that purely for convenience later on. And then because now I have this guy on top, and I have a 2, and then I have a to the 2/3, so that's 2am over h bar to the 2/3 power. I realize that is a bit messy. Let's go ahead and cancel out that. Let's get that out of the way. Now I have 2am over h bar to the 1/2. I have 1 over 2, and I have 2am over h bar to the negative 2/3. That equals 1/2. 1/2, I was gonna say, I wrote that wrong. That's not 2/3, that's 3/2. There we go. And that's to the negative 3/2. So 1/2 minus 2/2, or 1/2 minus 3/2. 1/2 minus 3/2. That equals negative 2 over 2, which is negative 1, meaning it is now just this. Or I get h bar over 4am. Now that's such a nice clean result that it makes me absolutely certain that I messed up the expectation value of the momentum before, because that's just far too nice and clean. Okay, so there's that guy. That's nice. We have our expectation value of x squared, which means let's just go ahead and take an extra step here. My sigma is, and I never remember what order it is, but that's okay. That's, you know, that's why we have stuff written down, so that we don't have to remember. Okay, so it is expectation value squared minus, so this one, so that's going to be the square root of this guy minus this guy. Yep. Which means that my standard deviation in x is just this square root. Okay, now we're done with that one. Yay. I'm getting near the end of the page. I'm just gonna go ahead and grab another page because I know that this next one is lengthy. Well, possibly only lengthy because I'm messing it up. I'm kind of holding out hope that I'm going to figure out what I did halfway through working it out for like the 5th time. I'm assuming it's just me not being careful. The first part is going to be trivial. So this guy is going to be h bar over I. So our momentum operator is h bar over I del x. That is the result that we got in our section about momentum here. There we are. So this is our momentum operator. is I equals negative h bar del x. I tend to prefer this way just so I can avoid that negative sign. There we go. That is our momentum operator. If I ever forget about which way that works, units. So h bar is joules over seconds, and then the derivative, joules times seconds, and then the derivative with respect to space is going to take out a spatial dimension. So a joule is a kilogram times a meter squared over a second squared times seconds is h bar. Del x gives us units of 1 over meters, and the result is kilograms times meters per second, which is momentum. That whole like unit analysis stuff that you did, and like I think most people go to whatever it is you do before high school, like junior high school, they probably drilled in unit analysis, dimensional analysis. You're still gonna need it. Okay, then we're going to have our, I should write out what A is. So that, I probably should have written it outside the integral. AM over h bar pi to the 1/2. Then we have e to the negative amx squared over h bar times del x acting on this guy. So we need to take that derivative. And it's not bad. So we just have the derivative of the inside times the derivative of the outside. I should actually write it out here. Here's where I started just, putting in a letter, because I didn't want to have to write all of that out each time. Like, seriously, it gets a little cumbersome, and it, at least for me, leads to me making mistakes. So I'm just calling all that junk B, just to differentiate it from my little a I did before. Okay, so my derivative of the inside is going to be negative 2 times b times x. That is now multiplied by my derivative of the outside, which is the same thing I had before. So that gives me my momentum is h bar over I, and I really should just replace all these constants with just a letter and put them in again, since I know I'm going to mess it up. But I just still keep doing it, so go figure that one. Okay, and then I get a 2 amh bar out here. Then I have inside this guy dx, and I have an x, and I have e to the negative. I got 2 of those. You'll notice that this is just the expectation value to x, which we found before was 0. So that's why I said this one is trivial. The expectation value of momentum is 0. Probably saw that one coming. Probably see this one coming too, that now this, so that's going to be squared, is not going to be a 0. Now we're going to have this guy. I really should just replace it with that b. And now we need the second derivative. Ooh, yeah, second derivative. Fortunately, we already took the first derivative, so yay. That takes away half the pain right there. And it's not a bad derivative. It's just that, you know, we got that extra step in there. Now we gotta do that whole, so if we have d dx of f times g, that's going to equal f times dg dx plus df dx times g. Ugh. I am going to be double checking my answer to make sure I don't mess up. So what I get here is I have f, we will say, well, first let's just pull out this negative 2b. We don't bother with that. So f is x, and then dg dx is derivative of the inside. That gives us another 2b times derivative of the outside, which is just that thing, plus df, which is 1. So I don't even really need to write that. And then g, so just this guy. Okay, so what I get if I simplify that is I get negative 2b times e to the stuff times x negative 2b plus 1. And oh yeah, to make it more confusing on myself, I was using a before, which is very silly. Okay, so I have 2b this minus 1, so I just got to swap around. Well, I believe my signs are right. Yep, that one ended up being, so we can write that as 2b x squared, and then we'll get 2bx minus 1. Yep. Alright, so all I did there was I just distributed my negative sign inside, by the way. So I just multiplied both of those by negative 1 so I could have this guy be positive in there. Or in other words, we get, so I already forgot what b is, we get 2amh bar e to the negative am over h bar x squared times 2am h bar x minus 1. Whew. Let's pull that out here. So I get h bar over I squared, this guy. So when I used to do tests, I used to just constantly name stuff as like C, a constant, as I would go, because I knew I was going to run out of time. So I would just have like this line of C1 equals this, C2 equals this, and then I just have like constants out in front. I kept redefining it as I went, and then I would never go back and reevaluate it because I was certain, like, I was just going to run out of time, so I didn't bother. Okay, those are all the constants we can pull out of that. And then I have dx. Now we have e to the negative 2am over h bar x squared. And we have, so we're replacing this. So we got this guy multiplied by all of this. X minus 1. There we go. Okay. So that means that I pull all that stuff out. We got this out front. So now I will have 2am h bar x times this guy. Now, fortunately, we already know that's going to be 0. Oh, I'm actually just multiplying that through, aren't I? Let's go ahead and do that. Okay, so our first term is just going to be 2am over h bar x times this. And then our second term is going to just be minus e to the negative 2ma over h bar x squared. Okay, so we can break that apart into two integrals. This one is just going to be the expectation value plus some junk out there, so that just equals 0. Already I think I figured out where I went wrong before, so hopefully this is going to simplify better than it did before. Let's go ahead. We're gonna keep that, and I probably could go ahead and roll those up. So I'm gonna put out this pi there. So then I have a 1/2 plus a 1, so that's 3/2. And then that's gonna be times that integral dx, we get a negative sign out front, of e to the negative 2am over h bar x squared. This guy, we did it before with our u substitution, so we can use the result that we had before, because that's going to be h bar over 2am square root times pi, square root pi. So I end up getting h bar over I squared, and we have a negative sign, which is fine because that's going to cancel out. I get 2am h bar to the 3/2. My square root of pi is going to cancel out. I'm going to go ahead and call this one 2am over h bar to the negative 1/2. Yeah, this is much cleaner than what I did before. Okay, so then I have h bar squared divided by -1 and a negative, so that just gives me h bar squared. And then we have 3/2 minus 1/2 just gives me 1. So that's going to be times 2am all over h bar, so much better. And I get 2am h bar. That simplified so nicely that it's either clearly correct or clearly a mistake. Okay, so then my sigma p is just going to be this guy minus this guy, which was 0. So my standard deviation in momentum space is this. And the reason we did that was so that we can do D, which is, you know, uncertainty principle. So I already forgot this one. Let's go ahead and copy that over. So part D. Alright, so part D, we want to know sigma x times sigma p. That is going to be h bar over 4am times 2am h bar to the 1/2. And what we get there, those cancel out. That turns into a 2. So that is going to be, or actually, yeah, that's a 2. I have a feeling that might supposed to be a 4. We'll see. So I get h bar over square root of 2. This is where I suspect I made a mistake and had an extra factor of 2, because what we expect from the uncertainty principle is that it's over h bar over 2. I don't know, usually we just say h bar because I play all fast and loose with that, when admittedly I should not. H bar over 2. Yeah, so I'm assuming I probably made a mistake somewhere. It's a reasonable assumption that in all these derivatives I did make a mistake. But that's fine. I just make a note. I am off by a factor of square root 2. Or maybe that's not supposed to have a 2 in it. Nah. There we go. So my result shows, from what I did, it would show that I'm a little bit too, well, it works. It's still, I wouldn't expect it to be exact. We're within the realm. I'm not sure if they wanted an exact one. The only physical system I know of that satisfies this exactly would be a simple harmonic oscillator. So my result is within possibly. My result, on the other hand, shows that sigma p, sigma x Instead of being h bar divided by 2, we are h bar divided by something smaller than 2. And if we divide it by a smaller number, so basically we're gonna have whatever like something times 10 to the negative 34 divided by square root of 2, which is like 1.14, versus something divided by 2. So I'm within my realm of the uncertainty principle. So we're still happy. That's my comparison. Probably want to write up some sort of thing to show that you understand how that works. And there you go. That's the end of that one. That is the end of chapter 1. No more chapter 1. Next is going to be separation of variables, and probably if you're in an undergrad quantum mechanics class, or if you're like, say, the last part of modern physics, chapter 2 is kind of like where all your meat of the class is. So it's a long chapter, and there's a lot of problems, and they are probably the most pertinent problems that you're going to face, at least in undergraduate quantum mechanics. So with that said, there we go. All done with chapter 1.